Hi, I'm Dave Thomas of the YouTube channel, the NMSR. I'm president of New Mexicans for Science and Reason, and I had an idea regarding the final experiment. I think the final experiment has done a great job showing the difference between what the sun would do in a globe Earth model versus a flat Earth model. And I'm in great anticipation of seeing how the results of that turn out. But I was thinking, what if there's a period of cloudiness where you can't see the sun? Would that be used to claim that the whole experiment was invalid? So I started to think about what other things could we look for besides the sun? And that got me to thinking about stars. And so I looked into, can you see stars in Antarctica during the period of the 24-hour sun? And I used to work at a earthquake instrument center here in Socorro, New Mexico. And one of my colleagues, DJ, has been to Antarctica numerous times. So I said, hey, DJ, tell me about Antarctica. Can you see the stars during the 24-hour daylight down there when you're working at McMurdo Station? And here's what DJ said. From my hikes around Observation Hill at McMurdo, I was able to snag a photo that had the moon visible in daylight. Unfortunately, I was there when it was 24 hours of sunlight, so I did not have any view of the stars except the sun spinning counterclockwise in the sky, which disproves they'd flown us to Greenland, by the way. This is the picture that DJ mentioned. This shot on the left is from McMurdo Station in Antarctica. It's on the other side of Antarctica from where you're going to be doing the final experiment at Union Glacier. But it's not quite as far south as Union Glacier. It's about 78 degrees. Union Glacier is almost 80 degrees south. But sure enough, just like DJ said, here is the moon sort of blown up there. And it's not unusual to see the moon in the daytime. In fact, the only time where you really can't see the moon during the daytime is near the new moon. And of course, if it's cloudy. So on the right here, I have a picture I took last month here in Socorro, New Mexico, showing during these summer months. Yes, we can see the moon even in the middle of the day. So that's not too surprising. So the next thing I wanted to look at was twilight. How do we know when it's dark enough to see the stars? What kind of twilight is that? So there are actually three classes of twilight, and there is daytime, and then right after sunset, when the sun is from the horizon down to 6 degrees below, that's called civil twilight. And it's really too bright to see stars during that time. The sun has just set, it's still almost daytime. When you get to the sun being from 6 to 12 degrees below the horizon, that's called nautical twilight. And the reason for that is you're able to see some of the brighter stars. And if you're at sea and you have a sextant and you want to find your position, what you do is you find a star and measure the angle from that star to the horizon. So it has to be bright enough to see the sea horizon. So nautical twilight is perfect for that. Dark enough to see a few bright stars, but not so dark you can't see the horizon. After nautical twilight, there is astronomical twilight, where it's probably too dark to even see the horizon. And then, and that goes from 12 to 18 degrees. Past 18 degrees, that's night. Yes, you can see stars during that time. So I pulled up this chart in December for my location, Socorro, New Mexico. You can see on December 1st, the sun will set at just before 5 p.m. Civil twilight, that first 6 degrees, ends about a half an hour later. Nautical twilight ends about a half hour after that. So that means you can start to see stars, after 5:30 up to 6 o'clock. About a half hour after nautical twilight is astronomical twilight. And then it's nighttime after 6:30 p.m. for a 5 o'clock sunset. So that's the situation for New Mexico. What is the situation going to be in Union Glacier Camp on December 19th to the 22nd or so at Union Glacier Camp? So we don't have civil twilight. We don't have nautical twilight. We don't have astronomical twilight. The sun is up all day. So I think that's a strong indication that the globe side expects no stars to be visible. So let's look at a little animation I whipped up. This shows um, the sun on a flat Earth model, and this is during the northern hemisphere summer. And the flat earthers say, well, the sun projects this beam of light, just like shining a flashlight on a wall. Some regions are lit up, some regions are in darkness, and that's how they define day and night. So this yellow region is day, the darker region is night. And this almost works in the summer. You can imagine the sun broadcasting this beam and having it cover that's almost a circular area of daytime. But let's look at this very similar chart. Here's what the sun does on the flat Earth in winter. And you can see that the region of daylight is sort of this big region with a big dark nighttime hole in it, the what I call the zone of darkness. So let's slow that down. Here is a still showing the sun over by India, and it's nighttime in Canada, United States, Mexico, all of South America, and presumably the United States and South America, they're just too far from the sun to be lit up. But way over here at Union Glacier Camp, just south of South America down there in Antarctica, it is lit up. That's what we know. So this is what that chart of sunlight would have to look like on the flat Earth map. So how does that happen? How can the sun be so far away from North America and South America for those regions to be in darkness, and yet Union Glacier Camp, even farther away, is in the daytime? So this got me thinking that Union Glacier Camp is far enough away from the sun during at least a good portion of the day there in Antarctica on December 19th or so. Union Glacier Camp should be far enough away that you should be able to see stars if the world was flat. If this flat Earth model of the sunlight only goes so far, and after that it's nighttime, if that's valid. So that was my idea. I've created a star sphere with Python, and I've got an actual star sphere right here. Basically, it's got the all the stars, and the stars go for millions of light years in all directions. What a star sphere does is it projects all those stars onto a sphere that surrounds the Earth in the center. So yes, here is Orion. There's the Belt, Rigel, Bellatrix, Betelgeuse, and down here is Sirius. So basically, star spheres allow you to figure out where any star is going to be. This here's the sun, this line up here, and because the sun is so close to Orion, that means In the summer, you can't see Orion. It's blocked by the sunlight. Orion is a winter constellation. So this is a simplified star sphere. In the northern hemisphere, I have Polaris and the Big Dipper. And then in the equatorial latitudes, you can see them on the far side of the Earth coming around. There is Orion and the bright star Sirius that's underneath it. And then on the extreme southern latitudes, there's the Southern Cross, which will come into view briefly just because of the angle that we're looking at here. There's the Southern Cross, Big Dipper in the north, Southern Cross in the south, Orion around the equator. So that is the sphere that we're going to be using to decide what stars can you see from Union Glacier Camp if you could see stars at all. So here is Antarctica. Union Glacier Camp is over on this side, south of South America. And imagine if you are lying on your back. I hope you have a blanket because it's cold down there. You're lying on your back, your feet are to the north, your head is to the south, pointing toward the South Pole over there, and you're looking straight up at the zenith. If you could see stars, and we don't think you should be able to see any stars in December, but if you were doing this in June, yes, you'd see the Southern Cross. Here's what you'd see if you could see stars. Here's the Southern Cross, and it's going clockwise around the zenith, which is straight overhead. Remember, your head is pointing toward the South Pole, your feet are pointing north toward South America. And this right here is the track of the sun. And up here is Sirius. They're very close to the outer rim of this diagram, which is the horizon. But the Southern Cross, that's high in the sky, plainly visible if it's dark enough to see stars at all. And importantly, it's going clockwise. So here is the flat Earth equivalent. And I don't know if this is published anywhere, but I'm assuming that maybe the stars are in the dome or maybe a flat disk. I've assumed just a flat disk for simplicity. But there are some constraints on the stars. If you're at the North Pole of the flat Earth, if you look straight up, you'll see Polaris. In the far northern latitudes, people can be looking straight up and see the Big Dipper. If you're at equatorial latitudes, you can look straight up and see Orion. And if you are at extreme southern latitudes, say Australia, New Zealand, even farther south than that, you can look straight up and see the Southern Cross. That's the setup for this next little Python animation, which has, there's the flat Earth, and here's our person. Again, his head is to the south, except for the flat Earth. The south is toward the outside of the Earth, and his feet are to the north toward South America, and he's looking straight up. So there's the setup. If you could see stars, and again, we think it'll probably be too dark, what will you see? Well, here is the Southern Cross going counterclockwise. It doesn't even get as far as the zenith. And so that's quite curious. So that is a, a major difference between the globe model and the flat Earth model is that the Southern Cross will appear to be going counterclockwise. It won't even make it to the zenith. It'll stay toward the south. So so that leaves us two potential kind of black swan observations that if either of these was observed, that would be strong evidence for the flat Earth side of things. The first one is, can you see stars at all? And if during that time of the final experiment, you can see the Southern Cross, that would be strong evidence for a flat Earth. And the second is, which way is that Southern Cross going? If it's moving around the sky counterclockwise and not making it to the zenith, that is also strong evidence for a flat Earth. So I think you might consider those as an adjunct to the already very interesting final experiment. The Southern Cross is visible, as these flags show, from all sorts of places, Australia, New Zealand, Chile, Argentina, all over the southern hemisphere. So in conclusion, there's a couple suggestions to consider for the final experiment. Can you see stars at all? And if you can, are constellations like the Southern Cross going counterclockwise? And either of those would be strong evidence for the flat Earth. So that's something to look for in addition to just what the sun is doing in that big circle around the horizon during the 24-hour sun. So we are just waiting with great anticipation here in New Mexico. We wish you good luck with the final experiment, and we will be watching with anticipation for how this turns out. Take care.